All right, let's begin. Welcome back. This is CS3510, L03B. The topic of today is median of medians. Quickselect. So what is Quickselect? Suppose we have the problem. Given A, 1 to n, find the kth smallest element. So we're given an array, unsorted. We want to find the kth smallest element. This is interesting. If k happens to be, if k is equal to n over 2, then what do we know about the element that we're finding here? Not quite the mean. It's the other one. It's the median. Yeah, it's going to be halfway. Suppose it's odd. It's that middle element, right? So there are many reasons we would want to find the kth smallest element. What's a really trivial way without, we could just end the lecture now if we found an easy algorithm for this. What's an efficient algorithm to solve this problem?
Sort it and pick the middle element.
Yeah, so sort, then return a k. That takes how long? Yeah. Okay, n log n. Can we do better than that? We can actually do worse than that. So first we'll do worse than n log n, and then we'll show you how to do better than n log n. The answer is basically this algorithm called Quickselect. Now, the way Quickselect works is it's just quicksort, but instead of sorting the whole array, it only just kind of does the pivoting, not to sort the array, but to look for the correct pivot point. So here's the way Quickselect works. It's basically, as far as you can think, similar to quicksort. We have A, L, U, and then we have an index k that we're looking for. So if L equals U, or whatever our base cases are, return A. Doesn't really matter. And then we're going to choose a pivot pi, again, by a partition function, which is exactly the same, for now at least. A, L, and U. Doesn't need k. It chooses a pivot for us. And then we have pi, again, is the index of the pivot element that has been returned. And at this point in quicksort, we would recursively sort everything below the pivot and everything above the pivot. But instead, we're going to do two cases. If pi exceeds k, like the index I, the pi is an index. So if the pivot we're given is above k, then we're going to recursively quickselect on the left half. And if it's false, if pi is less than k, we're going to quickselect on the upper half. Is that pi plus 1 u? And then if pi is equal to k, we're just going to return a of pi. Right?
Add k to the quick selects.
Oh, yes, thank you. Excellent. Yes. So why do these conditions work? If pi is greater than k, suppose we were in the case that we chose the pivot perhaps a little too big. Right? So we chose our pivot, let's say here. Something like this, right? If we chose the pivot such that the pivot exceeds this index k, we have, after a single partition, we've chosen the pivot is in the correct place. At this point in quicksort, we would normally sort everything over here and sort everything over here recursively. We don't need to do that, though. We're just looking for the kth item, right? From least to greatest, we're looking whatever is supposed to be an index k. Now, we could sort and pick that item, but we don't want to do that. So what we're going to do instead is that we know that if k is less than pi, we know that all these elements are also less than pi. So we know that k is somewhere in here, right? So we just recursively are going to go look over there instead of both sides. So we're not doing a double recursion this time, we're just doing a one-sided recursion, right? So we're going to go look over there. Now, in this case, let's suppose we chose our pivot too small. If k happens to be bigger than the pivot that's chosen, we know that k is somewhere over here, right? If k exceeds that specific index, then we know we're too big, right? So that's kind of, and we only learn, we choose the pivot perhaps randomly, and then we only learn what the pivot index is after the partition completes. That's placed in a certain spot. We don't know that before. After partition completes, it places this pith element in this specific spot, and then we can determine if k is less than or greater than that index, right? And using this recursively, we see that we do correctly get down to the brass tacks. We do find the element correctly, right? Before runtime analysis, any questions on the correctness? These pictures, that's basically the proof, right? So, questions on this? Okay, now the important part today. What is the runtime of Quickselect here? In the worst case, let's say we choose pivots really bad every single time again. We choose we repeatedly choose bad pivots. T of n will be a function of what? N minus 1, right? We don't nicely have to search over half. We search over basically the whole array each time, right? Plus, how much work is done at each level? Yeah. What is that?
N squared.
Yeah. So this is in fact horrible. This is in fact worse than the n log n algorithm. The worse idea is in fact better than this complex idea in the worst case, right? Now, what is the average case of such a runtime? Well, first off, what's the best case? Suppose we split it nicely, right? Suppose that each time pivots were chosen, this is the worst case. Let's do the best case, right? I don't believe in calling it that, but we'll do that. At each time, let's suppose we pick a pivot approximately half. What's our size of our subproblems going to be? A is what?
1.
Yeah, we only have one recursive call. We don't do both. We do one or the other. Kind of like binary search. We recurse on the left or we recurse on the right, but not both. And how much work is done at each level? Yeah, still O of n. So by the master theorem, we see A is 1, B is 2, and D is 1. What is that? Yeah. Log base 2 of 1 is 0. D is, well, we take that. Okay, done. Right. So in the average case is actually, not the average case, excuse me, the best case is O of n. Now, what about the average case? Okay, we could redo that whole thing we did. What was it? The T of n is going to be equal to 1 over n times the sum of I equals 1 to n minus 1 of T of I plus O of n. The difference here is there's no 2 there. I'm not going to repeat all that, but you could perhaps believe me, it's probably O of n. Maybe we'll put it on the homework. Repeat the analysis in the special case there. Instead of a doubling branching factor, it's a single branching factor, right? It's not too bad. Okay? Now, what's the point of, why are we doing this, right? It's not the case that in the worst case we want to select an element with n squared time, and then, like, on average, most of the time, similar to quicksort, we could choose it in O of n. That can be done most of the time. But recall when we did the analysis in quicksort. We mentioned as long as you chose an element in a greedy fashion, not a greedy fashion, but at least a non-constant away from the max and the min, you still got n log n, right? Right? You still got that, as long as you chose something that's not a constant away, right? Now, here's kind of what the point of today's lecture is. As long as you choose something multiplicatively away from the constants, from the max and the min, you have good runtime, right? You cannot, in the naive quicksort and quickselect, You cannot always promise, though, that you never choose the minimum, then the second minimum, then the third minimum repeatedly. You can get unlucky and always do that. But here is what you can, the moral of today's lecture. Median of medians chooses pivots better so that the new worst case improves to the average case. That's really all median of medians is, right? And again, recall you have something that looks like this, that's n squared, that's n log n, let's say, whoop, whoop. All you need to do is somehow choose pivots better. And if you can choose pivots better, then this part never happens, right? If you can choose pivots better, multiplicatively in some way, you never have to worry about this. So that's all median of medians does. Choose a pivot better, so you're guaranteed this quote-unquote multiplicative property. You get something that looks more like this and then this. As long as you can promise you're some factor, some fraction away of n rather than a constant from the max or a min, you're good. All medians of medians does is it tells you a way to choose the elements. It guarantees you a way with a little bit more work to choose an element that's a fraction away rather than a constant away. That's sufficient for us to improve Quickselect and even Quicksort's runtime from this n squared. We'll improve it to the average case. The average case is then the worst case, which is just O of n. So in fact, this can select faster than sorting. Once we do that, we'll have a linear time selection algorithm. Right? Questions on what we're going to do? Right. So why do you think it's called median of medians? Well, what we're going to do is we're going to get we're going to take the median of a bunch of medians. That's basically it. That's the whole algorithm. Suppose we have our array here. It's really big. What we're going to first do is chop it up into blocks of size 5. Now, why 5? It's going to make sense in a second. We're going to then arrange each quintuple of elements into a subarray of size 5. So this is going to be A1. This is going to be A5. Then the next array is going to be A6 to A10. Okay? And this is going to be our A of n, right? Something like this. Now, what's the dimensions of this? Let's put everything in an Excel sheet. What's the dimensions of the Excel sheet? The grids, the cells here. How long is it? Yeah, this is like approximately, this is like n over 5. And then what's the depth of this table? Yeah, okay. So step 1, sort each column. How long does that take? Actually, we'll come back to the analysis. Let's do the correctness first. We're going to sort each column, right? So these elements are going to get swapped around. Whatever, right? Then, what do we know about the middle element here? Yeah. You have 5 elements. If you sort the 5 elements, the middle element is the median of that column, okay? Then you're going to sort, and this is going to be done recursively, the columns by the medians. So the next thing you're going to do is you're going to reorder the columns so that the medians are in a sorted order, right? So the medians will be sorted. The elements are not promised to be sorted at all, but the median of each one appears in the middle, and then you order the columns based upon the medians, right? So the whole column is going to move around. Now there's no promise anything else is sorted except this middle row, which is going to be the medians, right? Now this element in the very middle here, the middle column, the middle element of the middle column is the median of the medians, right? Now we need to ensure that this is a good choice of a pivot. That's all we need to do, right? What properties do you know after we've done both these sortings? What do you know this middle element has properties? What are properties of this? Yes?
At least 1/10 of the list items, all of the, actually, it should be roughly a quarter of the elements. Everything in the bottom right corner is guaranteed to be larger than it.
Yeah, absolutely.
It's quadrant, not corner.
Yeah, let's look at this box here. You know, let's look at A of n, for example. You know A of n in this row of 5 is not the median of that column. You know it's less than the median, right? So you know it's less than that element here. You also know that by the fact that these are sorted, this one is less than this one. Agree? So we know that in fact by transitivity, if this is less than this, and this is less than this, then this is less than this. So in fact, this entire quadrant-ish area is greater than or equal to the median m, right? This is some set here. How many elements are in this quadrant? What's kind of the area of this quadrant? So we're going to have, first off, this middle row here, right? The size of that row is going to be what? This is geometry. Sorry, what? N what?
Dash 4 minus
N dash?
divided by 4,
Oh, I see. N divided by,
because it's 4 quadrants.
well, the quadrants are area. Right? So let's just measure the height. Let's just measure what's the length of this thing? It's going to be n over 5 over 2. Because n over 5, that would be n over 5. So it's n over 5 over 2. So it's n over 10 minus a single element, right, for that middle, right? Times, plus the area of this, which is approximately 2 columns. So it's going to be 2 columns. 2 times what? N over 10 as well, right? N over 2, N over 5, N over 5, half of those, right? So whatever this is like kind of like, and then again, what if it's not a multiple of 10 and so on, right? It's approximately what, though?
3n over 10.
Yeah. Now what about this whole thing? By symmetry, we know we have a bunch of numbers here. We know that this also is going to be, the same way m is approximately less than 3n over 10 of the elements, we also know that m is greater than 3n over 10 of the elements. Right? So in fact, if m is greater than 3n over 10 of the elements, we can say something about the range that m lies in, which is what? What is the actual range? It's kind of in the middle. The middle, we can't say a third exactly, and we will need the actual fraction.
A little 2/5.
Sure, but what's the lowest m could be?
3/10.
Yeah. So m is between 3/10 and what's the largest m can be?
7.
Yeah, it's 7/10. Right? So if we run median of medians, we can always, the important thing though is like, that's not like n over 2 or n over 3 or something. That's just, but that's definitely not a constant away from the min or max. So if we run median of medians as a pivot choosing strategy, we can choose a pivot guaranteed that is a multiplicative factor away from the ends. So it's closer to the middle by a multiplicative amount, again, as a function of n. It's never going to be 3 away or 5 away from the max or the min. So median of medians, first off, does give us an element that has our correctness property, right? But it takes some time. How much does this really take? And again, I said we sort the middle elements, but we don't really need to do that. That's just kind of a visualization thing, right? In fact, we just choose the medians of these of each of the things. How long does it take to sort each column of size 5? Yes. So each column, and let's say it takes 5 steps. But how many columns are there? Yeah. So that's just O of n work to sort the columns, right? Then how much time does it take to find the middle element? This is a trick question. Yeah.
If it's for one column, I feel like it's O1 because you're just finding the middle element because they're all the same size.
Yes.
If you're finding for all the columns, it would be O of n because there's n columns. Oh, sorry.
Suppose we don't want to sort them. But now we have, in some fancy way, the medians we have n over 5 medians. We want their median. How do we find that? Yes?
Use Quickselect.
Almost. It'll be the other way around. We want to use medians of medians to help Quickselect. And it's kind of funny that Quickselect can be used to find a median, but you run median and medians to find a pivot for Quickselect. So you'd end up with an infinite loop and you'd get stuck something there. The answer I'm kind of looking for is recursively, right? The median, the medians, this is a median finding algorithm, right? So you just find the medians. So it's going to be like something like T of n. In the worst case, m is between T of what? 7n over 10 plus O of n, which is what's that going to be? Without using the master's theorem, which finding your A, B, and D, you should be able to quickly say, well, we don't have 2 subproblems and things are shrinking pretty fast, right? But things are still shrinking at a multiplicative level, but we don't have 2 subproblems. It's going to end up being the same analysis there. Instead of B equals 2, it's going to be B equals 10/7. So we're going to have, what is that? Log base 10 over 7 of n is just going to be, log base 10 over 7 of 1 is what? 0. Yes, and then, and then D is going to be equal to 1. So we see that D is the case. So then T of n is then what? Yes. Okay. So this partition still takes us linear time for us to find a pivot in an exotic way, right? The partition runs recursively. Quickselect also runs recursively, right? So what we do here is then we're promised that as long as we find this partition, we get this kind of analysis and not the worst one. Questions on median of medians? Yes?
Explain that n over 10 minus 1 plus the 2 times n over 10.
Right. So it's just kind of, when you're doing it on a whiteboard, it's kind of difficult to say. But suppose we did organize the elements in this way, right? With this property that each of the rows is sorted and that the columns are sorted by the median, according to the medians. Now we don't actually want to do that. But just suppose for visualization that's true. It's the case that each of these elements in this upper quadrant is less than this median, and each thing here is below this is less than this greater than this median. And this is less than this median, right? So we just are kind of like guesstimating the area of this to say what fraction of it is greater than it. We already do know that it's a fraction of the elements. It is like you could just look at it and be like, that's approximately a quarter, right? That's approximately a quarter of n elements. That's approximately a quarter of n elements, but like, to be a little more careful, we have 2 rows here, each of size n over 5, half of that. Because this is the length n over 5, so half of it is n over 10. So 2 n over 10s. Then here, we have an n over 10 without 1, because we have the median, suppose it's odd. So that's that one plus that one. So the sum of those 3 rows is going to be approximately that. We get approximately 3 n over 10. If you said a quarter, I'd forgive you. I mean, it's like, look at that. It's a quarter of the elements, so. More questions? Okay.